All right, guys, welcome back. We're going to continue our discussion of BGP. We did a basic BGP introduction on the first time around. Now we're going to get into BGP operations. We'll look at some command line stuff in this lesson here. It's probably not going to take us 2 hours. I would say probably an hour to an hour and a half at the most, but we're just going to continue with our discussion about what we talked about the last time, which is our BGP operations. So let me go ahead and pull up our notes from last time, and we'll continue to kind of take notes in our BGP overview discussion. And I'll add to this as we kind of go through the lesson here. We're going to take a look at basic BGP operations. We're going to talk about how BGP autonomous system numbers work in this case. There's two different types of BGP autonomous system numbers that exist. We'll talk about kind of an introduction to BGP peering relationships. It's actually a very complex policy-based decision, complex situation with how BGP peers are established. It's not going to be anything like our standard IGP process, where we turn on the routing protocol on the link at the link level, and then the routers find each other and establish their adjacency automatically. In the case of BGP, there's a lot of different things we have to consider before we actually turn on our BGP peerings and take a look at those peerings. Ultimately, it's those peerings and the peering relationship that dictates how traffic is going to be forwarded, depending on whether we're dealing with, say, an external BGP peering relationship versus an internal BGP peering relationship. So there's a significant difference. So we talked about this a lot, and I'll mention it even a few more times in this case. There's a significant difference between an IGP routing protocol that has its own transport versus BGP running over TCP with its own basic application. All right. So we'll talk about that. So, when we talk about BGP being an application as opposed to a traditional routing protocol, because BGP doesn't have its own transport, it relies on underlying IGP protocols, or at least some sort of IGP routing process to provide the transport for the BGP data. All right, so we'll take a look at that. We'll take a look at how that works. We'll do some packet captures in this particular lesson. We're not going to build our entire BGP domain just yet. We're going to be doing a couple of other things with BGP before we actually get into looking at some of the advanced features. But I'm going to be talking about what those peering relationships are, what some of the requirements are for peering relationships, and so on. Before I actually get into that, though, let me backtrack a little bit about what we talked about with regard to the fundamentals of BGP. And one other thing I want to start to talk about in this particular lesson here is what are some of the concepts with regard to the different message types that BGP uses in its peering relationships. And we'll take a look at that when we get into our packet captures and identify through those packet captures how we can see that information. All right. BGP is incredibly unique, especially if we compare it to all the other routing protocols. It's our exterior protocol, like we talked about, and it's what we use to connect our autonomous systems around the globe. All right, and we'll see as we continue to dive deeper into BGP relationships and how BGP functions as an application, why it's so different. Now we're going to start with a really basic topology in this case. Eventually we'll add more routers to this topology, and we'll kind of build on this to talk about different BGP attributes and route propagation and route recursion and so on. But in our lesson today, we're going to focus primarily on establishing an eBGP pairing relationship between router 4 in ASN 4, actually ASN 4.4, and router 5 in ASN 5.5. And we'll build on this, right? BGP is a really, really complex application. So we kind of have to build on our knowledge and understanding of BGP in order to ensure that we have that foundation that you're going to need for the CCIE written and the CCIE lab. All right. We talked about this a little bit as well in our last discussion. With BGP, there is no such thing as forming a neighbor relationship with a bunch of devices in the same segment automatically, right? For devices in BGP to be able to peer, it does this by using a single peer-to-peer relationship, which we refer to as BGP peering. And we'll talk about this in more detail as we go through the lesson in how we utilize TCP port 179 in a client-server environment with the SYN-ACK process to be able to establish this peering relationship before we go to our BGP Open and we start doing our capabilities exchange and start learning more about how BGP operations work as we go through the routing process. As we talked about, and I mentioned it a few times, BGP is an application layer protocol. All right. A lot of engineers would say, oh, it's a routing protocol, right? It's like OSPF, it's like Eigrp, it's like ISIS, but actually ISIS is kind of unique too because it works at layer 2 of the OSI model. But BGP works at layer 7, and it runs on top of TCP using IP as its transport, okay? As an application layer component, BGP does something that other protocols don't. RIP is very similar in the use of a transport layer protocol in establishing a RIP routing domain information, but BGP leverages TCP, right? So if we look at a Eigrp datagram or we look at an OSPF datagram, the protocols there have reliability mechanisms built into them through the use of things like RTP, the Reliable Transport Protocol, sequencing and acknowledgments and so on built into the protocol. In the case of BGP, we don't have to worry about that because we're running on top of TCP. So we don't have to engineer all of that reliability and all of those reliability mechanisms into BGP as a protocol because it relies simply on the communication, the reliable communication, if you will, of TCP, specifically TCP port 179, right? You think about your routing protocols, there's going to be value in how routing protocols make decisions with routing protocol metrics and so on. This is another unique case with BGP. Metric is not really calculated that way. And we talked about this in our very first BGP lesson. BGP uses attributes instead of a single metric. One of those prime attributes, and we'll get into this in more detail. We're not going to get into it quite yet, but we will look at the BGP path selection process as a separate lesson because it's so complex. But one of those path selection process values is called the AS path attribute, which is essentially a list of all the autonomous systems that a prefix has to transit in order to be able to reach the destination. All right. Basically, it's just a recording of all that AS path information. It's not really critical to the function of BGP, but it is why BGP is often referred to as a path vector routing protocol as opposed to a standard metric-based routing protocol. All right. It's not distance vector, although a lot of people will equate distance vector attributes to BGP because of the way it goes from one autonomous system to another. All right. So I mentioned before when we were talking about BGP originally that a lot of engineers will kind of equate BGP to distance vector from the perspective of going from one autonomous system to another because we don't really have any visibility of what's happening within the autonomous systems. We only have visibility with what happens between the autonomous systems. But truly, BGP is a path vector routing protocol. All right. All right. Now, there is a attribute that we'll talk about. There's actually several different attributes that we talk about called loop prevention mechanisms. Well, one of them is a loop prevention mechanism where we look at the AS path attribute, and if we see our own autonomous system in that AS path, we get concerned that there could be a loop in the communications. Another thing that makes BGP different than everybody else is that when we do form our peering relationships within an autonomous system, that relationship is different than if we form relationships between different autonomous systems. And our next lesson will get into all of the details of the differences between iBGP peering relationships and eBGP peering relationships. We'll talk a little bit about that in this lesson here as well. All right? So when we're forming a peering relationship between autonomous systems, that's an exterior relationship. But we do distinguish between iBGP and eBGP because there are different operational characteristics that need to change based on how that peering is done, right? For example, we stated that there's an AS path, which is just the recording of those autonomous systems that we're transiting to reach a destination. Over an eBGP peering relationship, when a prefix gets sent from one autonomous system to another, the sending AS has to put its own autonomous system in the path. In iBGP pairing relationships, the prefix remains within the AS, so we don't actually insert that particular value. All right? So the rules do change. That's why we have a whole lesson dedicated to understanding what those rules are when we're talking about iBGP versus eBGP. All right? We're not going to get into that quite in a detail in this lesson here, but we are going to get into it, I promise. So let's go ahead and add to our notes here for some of the basic concepts. The next basic concept I wanted to talk to you guys about, because we're now getting into the operations, are Bgp message types. All right? Just like in OSPF, where we have things like link state advertisement or link state update, link state acknowledgement, link state request, DBD and so on, hellos and so on, or Eigrp, update, query, reply, acknowledgement, and hello. We have message types within BGP as well. As a protocol, BGP is a pretty complex routing application protocol. But we can't really learn the entire story of BGP in just one lesson. But the primary purpose of BGP is to control prefix propagation within the application. That's its primary goal, is to disseminate prefix destination information through the process with the properties of or policy that we've established for those particular prefixes. The protocol itself is not very complex, as far as how we establish adjacencies, how we maintain those adjacencies. But when we get into the actual policy propagation and policy generation and creation, that's where it gets a lot more complicated. All right? So there are essentially really four major BGP message types. Some people classify a fifth one. I will classify the fifth one. We'll talk about these, and we'll see them when we get into our packet captures. And as we go through more and more of these BGP lessons, we will talk more about these different message types. All right? So we'll start by taking a look at an open message later today and kind of breaking that down. That's where we do our capabilities exchange and we identify whether or not we're able to even peer with a BGP speaker and so on. All right? So these are the 5 essential message types that exist in BGP. And we will, like I said, get into the details of each of these piece by piece. Remember, the first step in BGP is that 2 BGP speakers need to form some sort of peering relationship with each other. They're going to rely on TCP, specifically the SYN-SYN-ACK process. All right, we know there's going to be a 3-way handshake because it is TCP-based communication. What happens after that, though, is the devices exchange something called an open message. The open message contains really, really critical information in order for these BGP speakers to be able to establish an adjacency. One of the key components of, outside of attributes and capabilities, one of the key components of the BGP open message is the autonomous system number. All right, and that's essentially what's going to allow us to determine whether or not this is an iBGP peering relationship or an eBGP peering relationship, is that autonomous system number. And the configuration is actually very similar. There's nothing that you configure within the BGP operations to suggest that this is eBGP or iBGP. It just happens to be what ASN, the client's advertising in its open message, and what ASN, the server, is responding with in its exchange. All right. When these open messages get exchanged, the speakers start exchanging keep-alives. All right. It's basically just a mechanism, in essence, to make sure that the other device is there, that it's healthy, that it's happy, that the pairing relationship can be maintained, and so on. If BGP speakers have updates to share about prefixes or prefix reachability or network layer reachability information about destination prefixes, that's where the updates are going to come into play. All right. It's very simple, and we'll see this as we go through our packet captures. If anything goes wrong within BGP, there's only one message type that's going to identify if there's an issue with the BGP pairing, and that's a notification message. In most cases, notifications will result in the teardown of that pairing relationship or some other error that's going to happen in BGP. All right, now I did happen to list the fifth one here, which is a very interesting BGP message. This route refresh message type, which again, a lot of people don't tend to classify as a standard BGP message type. It wasn't in the original standard, all right? It was enhanced, or it became a part of an enhancement later on. One of the things we talked about in our original BGP discussion was the extensibility of BGP, right? Its customizability and the ability for us to be able to enhance the protocol through different operations or different RFCs or whatnot. It wasn't in the route refresh wasn't part of the original BGP standard, but most major networking vendors do support route refresh behavior, which allows BGP peers to update attributes and routing information without having to tear down the pairing relationship itself. And that's really critical in the case of BGP because it is a relatively slow protocol. It requires a lot of overhead to process these large databases and this large routing information. So it is pretty important that we have a way for us to exchange changes in the topology and in the network layer reachability information without having to tear down this session. Okay? We're going to see what these message types look like in a Wireshark capture. We'll break them down. We'll establish an eBGP pairing relationship between router 4 and router 5 in our topology. And then we'll continue to build on that as we go through the process. All right, so let me just make a couple of notes here. Basically used to exchange capabilities information, timers, etc. ASN, I should add ASN here because that's a pretty important one. Keep alives used to maintain the TCP session and make sure it's healthy. Update used to send NLRI, what we call network layer reachability information, attributes, and prefix information. And then we have notifications, errors, right? Now there's many reasons why you would get notifications, and we'll get into troubleshooting BGP a little bit later on. But it's something that we'll get into a lot more detail. The route refresh is to exchange changes in network layer reachability information without having to, let me make sure that's spelled right, without having to reset pairings. All right, pretty important stuff. All right, now the next thing I want to talk about is the message format. Again, something we will see in our Wireshark captures, but we want to learn about all the operational characteristics of BGP by looking at the different message type, but we'll take a look at them kind of in more detail here. All right, and again, like I said, we'll take a look at this stuff in Wireshark, so I want to kind of preface that by just kind of going through it. All right, Each BGP message is going to have a header. So there's going to be a header for each BGP message. We'll see that the header will be basically marked as a 3 different fields. We've got a field that's called the marker field. We've got a field that's called the length field, and we have a field that's called the type field. All right. The marker field is 16 bytes in size. It's basically always just filled in with all ones. I think we'll see that in our Wireshark capture. So that's a field that we don't typically talk about too much. The use of the marker field was really just deprecated in some of the newer standards. So it was something that was used in kind of the original version of BGP, but not so much now in the modern versions of BGP. The original idea with the field is that it can be used to detect things like loss of synchronization between peers, and it also could potentially hold maybe authentication information if we're doing some sort of BGP authentication. All right. Why is this field even here? Maybe if you want to do some sort of backwards compatibility with really old platforms or platforms that are running really old versions of BGP, you might want to keep that information. All right. If you see the other fields, right? The more important fields, actually, the length field, very simple. Let me make some notes here. The length field obviously defines the length of the BGP message. And it's pretty simple. The type field, though, indicates what type of message you're dealing with. So the type is what kind of BGP message is this, right? Based on those original ones that we talked about. So for example, if I see a 1 in this field, we're dealing with a BGP open. All right. 2 would be, what is 2? I believe 2 is an update. We'll see this in the Wireshark capture. 3 would be a notification, BGP notification, and 4 would be a keep alive. 4 would be a keep alive, BGP keep alive. And then finally, the only one left, BGP route refresh would be number 5. So just like OSPF, 5 different message types, just like Eigrp, 5 different message types, obviously different, but similar in the fact that we have 5 different message types. All right. Now what follows the header information is the data itself. There's obviously an important exchange that's going to happen with the keep alive. There is no data required in the keep alive message, so you're not going to see any payload information in that particular case. All right, but if I want to form a BGP pairing relationship with another device, I'm going to send an open message. All right, now let's talk about specifically what's in that open message. A BGP open is going to have fields like a version. It's going to have AS, my AS. It's going to have a hold time. It's going to have some sort of BGP identifier. We'll talk about that a little bit later. There are going to be some optional parameters as well in that open message. Like I said, we'll take a look at these in Wireshark and kind of break them down. Most of the fields we're not really too concerned with. There's not a whole lot we can do with those particular fields, but there are some very critical fields that we would want to look at if we're trying to troubleshoot or identify issues with BGP. Okay? When we look at the open message format, there is a version number. All right? For BGP, we know that there have been several different key iterations of the protocol itself. So we need to make sure that we're compatible with regard to the extensibility operations that BGP has. Your system is also going to send out its own AS in the open message. So this is what's going to identify whether or not this is an iBGP or an eBGP relationship. There is a hold timer value. The timers, unlike OSPF, are not mandatory with regard to them being synchronized. They're negotiated. So I'll demonstrate that when we go into our configuration. All right, but if the hold timer value identifies, essentially how long we're going to maintain this relationship, what's interesting about the hold timer is that when a router that you want to peer with gets this information, it's going to look at that hold down timer, it's going to look at its own configured value. If they don't match, it will use the smaller of the two values. All right, the hold time needs to be either 0 or at least 3 seconds, okay? We can negotiate that hold timer to 0 if we need to, but we typically wouldn't set it that low because we could end up resulting in some flapping between the peers and so on. All right, then there's the BGP identifier. This is basically your BGP router ID. It's going to be able to distinguish your system uniquely within the BGP autonomous system. So the BGP identifier is a BGP router ID. The router ID is selected in BGP the same way as it is in all the other IGP processes. It can be manually configured, which trumps every other option, or it will take the highest active loopback IP or the highest physical interface IP. All right, now it doesn't have to be an interface that's participating in BGP. The status of the interface has to simply be up. That's the most important concept. All right, we also have optional parameters that can be sent within the open message. There's an optional parameter length and then the parameters themselves. That's what gives us that extensibility within the protocol and customizability within the protocol to be able to do interesting things. Another important message type, the last one we talk about really before we start to get into some of our configurations, is the BGP Update Message, right? Actually, we'll talk about the refresh a little bit later on as well. All right, now with the update, we have different structures. Let me write this down here. So with regard to a BGP Update Message, we have withdrawn routes length. We have withdrawn routes. We won't see all of these in our discussion today, but eventually, as we go through the process of learning more and more about BGP, we'll get into these in more detail. Attribute length. And we've got path attributes. So we're sending information about the prefixes, and then we have our network layer reachability information. Okay. Each one of these obviously providing different components. Basically, we're trying to indicate, some sort of indicator for withdrawn routes length. That's going to actually ensure that the update message is the vehicle for the routes to be withdrawn from the BGP table. And then we'll see a list of all the withdrawn routes inside that update message. We can contain fields that are used to share prefix information with peers, attribute information. Of course, we're going to spend a lot of time talking about different attributes that get associated with prefixes. You recall that this is a policy-based protocol, application, I should say, and we're making decisions based on policy. It's those attributes that allow us to make up those policy decisions and how we're going to route to a particular network, right? There are well-known attributes. There are optional attributes. There are non-transitive attributes. There are transitive attributes, and so on. We'll discuss the difference between those in another lesson because we still have to go through the whole path selection process. We still have to discuss all the different individual attributes. For example, a well-known mandatory attribute would be AS path, all right, which is, again, just a list of the autonomous systems that we had to transit for a prefix for reachability, all right? There can be many different attributes that are utilized in making policy decisions, and so we have different fields in the update to identify that we might have different attributes that are used. The network prefix information itself is located in the NLRI field. That's where we have the network layer reachability information. All right. Why did we not simply name the network layer reachability information field the IPv4 prefixes field? Because BGP is extensible, right? Meaning that it supports MPLS, it supports IPv6, IPv4, and if network information changed, we still want to be able to identify that field to carry that information. So we didn't want to tie it down specifically to IPv4 in this particular case. All right. BGP is built to start immediately with all these different protocols. We can carry VPN v4 addresses for MPLS VPNs. We can carry IPv6 addresses. That's where the SAFI and the AFI information comes into play. For BGP notification messages, there's only really two things within a BGP notification. And that is, we've got an error code as one of the fields, and then we've got an error subcode, and then we simply have data, right, to carry information about the notification. All right. So it's not hard for us to remember, what the purpose of BGP is. In this particular case, I think it's pretty simple. The error code simply identifies, a particular error, and then we might have a subcode that indicates that there's a different type of error. We'll get into some of the troubleshooting to where we can identify some of the common error codes and subcodes that we would see when we're trying to establish BGP pairing relationships. All right. It's BGP it's very complex when it's establishing peering relationships. So we do need to be familiar with some of the common issues that can occur, which we'll go through as we kind of go through a lot of our different lessons. Now, with regard to Bgp Neighbor States, this is something we always concern ourselves with when it comes to dynamic processes as well, right? In OSPF, for example, we have the down state, the init state, the two-way state, the exstart state, the exchange state, the loading state, and the full state, right? Well, guess what? In BGP, we have different operational states as well. All right, we can learn a lot about operations of BGP by examining those BGP messages, taking a look at their specific formats, and looking at the various states that the peers are actually transitioning through in the process of establishing a full adjacency. So when we really analyze the protocol, you're not really going to be surprised to see, and you'll see this as we go through a lot of our lessons, there are many different components built into BGP for stability. All right, just like any other routing protocol that we learn about, the process of BGP is really no different. There is one major significant difference though. IGP protocols like OSPF and Eigrp, they're designed to be to be able to converge as quickly as possible. All right. So if there's any kind of change inside the network, we want to achieve that sub-second convergence, so we know about that change immediately. On the other hand, BGP engineered completely different. The timers have much longer times, much longer durations than we would see with our IGPs, because we want to add or enhance the stability at the detriment of speed of convergence. If you understand what I'm saying, we'll see this as we start to configure BGP. It's as we refresh neighbors or we reset neighbors, reestablishing adjacencies can take a little bit of time, right? Primarily has to do with the fact that we're just dealing with really, really large routing tables in service provider environments and so on. All right. Instability in this type of environment could really cause a lot of issues with convergence and so on. All right. So there are several different neighbor states. Let's go through those, because you definitely need to understand these neighbor states in order to be able to identify potentially what's happening with BGP. Let's see, active, and we'll see some of these states actually today. Open sent, open confirm, and finally established. All right. Now, there is an idle state. This is essentially where the device has, it's not initiating any of the other states. It's actually not a good state. And then finally, we have the established state, which indicates that we're fully established with the peer. There are these in-between states of connect, active, open sent, open confirm, where we kind of go through these transitionary environments. So let me make some notes here. The idle state means that we are just kind of, this is not the best way of describing it, kind of stuck in the beginning, right? We're not trying to establish a pairing relationship with another router, spelled beginning, yeah. Maybe it's because we have a incorrectly configured, remote AS number, or there's some access list blocking TCP SYNs or SYNACs or whatever. Establish, of course, meaning that we have a full peering relationship. That's where we really kind of want to be. In OSPF, we talked about all these kind of transitionary states. Well, we have the same thing with BGP. Say, for example, connect. This is where the BGP speaker is waiting for the TCP connection. All right, to be completed. So maybe we have received some sort of TCP SYN request, or we've started the process of establishing the adjacency. Now we're waiting for that process to be completed. The active state means that we are actually trying to initiate a TCP connection with the peer. All right. In the open sent state, we have sent an open message, and we're basically waiting to hear back. Waiting to hear back from the neighbor. All right, and open confirm, the speaker, the BGP speaker in this case, is actually waiting for the keep alives based on successfully exchanging those different open messages. So we're waiting for a keep alive, but we have already exchanged open messages. All right. So that's those are the basic message types. Now again, we'll go through the whole process of identifying these as we start to build our topologies and we get a better understanding of how we're establishing these adjacencies and so on. But we can see a lot of this information in all the state information in some very basic show commands. One of the most common show commands that we'll see is something called show IP Bgp Summary. All right, where we might see in that particular output the peering might be in an idle state, and we might have the pairing relationship configuration done, but when we specified an invalid autonomous system number and so on. I'll try to duplicate as many error conditions as I can so that if you do see those on the lab, you'll have a way of kind of identifying that information. Okay? So we do have a couple more things to talk about before we start getting into our configuration and going into more detail here. All right? But as you can see from all this information here, there's a lot of things that we need to consider before we turn on the peering, because the peering itself is going to identify how we deal with BGP information. All right? Now, we did mention briefly about autonomous system numbers. We need to talk a little bit more about these ASNs based on a couple of routers. And the ASN, by definition, if you go look at the RFC, they identify essentially an autonomous system number as a way of identifying routers that are participating in the same domain under a single administration. I'm paraphrasing, but that's essentially what it says. All right. With the case of some organizations, though, they might have multiple autonomous system numbers in their topology. Maybe they acquired another organization, and rather than merging those autonomous system numbers together, they decided to go ahead and keep those separate autonomous system numbers and essentially set up an Ipbgp pairing relationship between those different ASNs within their own domain, single administration domain. So for me, I tend to like to classify ASNs as a separation of routers into a policy domain rather than a domain under single administration. So all routers that share a common policy will be part of a same autonomous system number, and then we'll have external policies that we define when we're going from one autonomous system number to another. Okay? These ASNs are allocated by the IANA. You can go to iana.org/numbers, and this is where you can apply to get an ASN, and then you would go to your local regional and internet registry to get that ASN. There are a bunch of requirements that you have to go through, though, before you actually get an autonomous system number assigned. All right? So let's talk about the ASN. We'll make some notes here about the autonomous system number. And we'll see this, let me just put in here ASN. We'll see this as part of our discussion when we do our configuration as well. Originally, this was a 2-byte number. And it went from 0 to 65,535, all right, to the power of 16. And then they further identified public versus private ASNs. You had your public ASN range, which went from 1 through 64,511, and then you had your private ASN ranges, which are basically ones that you could use arbitrarily without routing them to the internet, and that would be the remaining range, right? So your private ASN range would be somewhere let me see, private ASNs would be 65,000 or 64,512 all the way up to 65,535. All right, so that's what I think, like 1,023 different ASNs or 1,024 different ASNs. All right, so the last 1,023 numbers are your private ASNs. They're not available for allocation to end users. They can be used internally. All right. The issue that they had with these traditional values is that they ran out of ASNs, or they had the potential of running out of ASNs relatively quickly. So now, in the newer versions of, newer implementations of BGP, we have a 4-byte field. And I think that's, if I'm not mistaken, that is BGP 4-byte RFC. I think that's RFC 4893. Yeah, RFC 4893. BGP support for 4-byte or 4-octet autonomous system numbers. This RFC kind of describes the whole concept of how we deal with 4-byte numbers, because we still have to have backwards compatibility with our 2-byte brethren, right, if you will. Okay. In Cisco, it's been supported for quite some time, supported since, gosh, 12.4, I think. I'm going to go out on a limb here. 12.4.24T, I think it was. I think that's what I read the other day. All right, so let's talk a little bit about this 4-byte value and how it's represented. We'll talk about how we can configure that. But when we're dealing with a 4-byte ASN, there still has to be some sort of backwards compatibility with the 2-byte ASN, because we might have other routers that don't support the 4-byte field, although it's going to be pretty rare in this case. With the 4-byte value, we're looking at ASNs of 0.0 all the way up through 65,535.65,535. This notation allows us to have that backwards compatibility because the last half is essentially the original 2-byte ASN. We do have to have backwards compatibility with the old code. When they first implemented this, there was a big issue on the internet with this because there was an issue with some routers not understanding what was happening in this particular case. I mean, this is a long time ago. We don't really have to worry about this too much these days. All right. The 4-byte ASN supports, the fact that we support the 4-byte ASN, that's going to be negotiated in the capabilities exchange in the BGP Open. We'll see that in our packet capture. All right. Old BGP speakers will send AS dot numbers encoded simply as ASN 2, 3, 4, 5, and 6. The real AS path gets encoded with optional transitive attributes. Like there's an AS4 underscore aggregator attribute. There's an AS4 underscore path attribute. That basically allows us to tunnel AS path information and path value information through the devices that don't support the 4-byte value. Like I said, not something we're going to have to concern ourselves with. Certainly not on the CCIE. You're not going to have to worry about supporting old or legacy 2-byte values. You might still be able to configure BGP, or it might in fact be configured in the system as a 4-byte or a 2-byte value, but that doesn't mean that you're going to have to, deal with some sort of compatibility issue within the lab, within the scope of the lab. All right, there is a private range that you can use for BGP ASs but it doesn't really matter what autonomous system number that you use, as long as you don't try to route globally on the internet with domains that are not supposed to be, or ASNs that are not supposed to be used by you publicly anyway. But typically we try to avoid the use of public ASNs regardless, because we don't want to have issues with potential issues with routing over the internet. All right. Like I said, one of the loop prevention mechanisms as well built into BGP is if I find my own AS in someone else's route, I'm not going to be able to accept that route and use it, because that means that there's potentially some sort of loop. All right. Now, what about these peering relationships? Establishing BGP peering. We already talked about different message types, different neighbor states. What do we do with regard to different messages? But unlike BGP, unlike standard IGP, like I said, doesn't have its own transport. Now, what that means is that you don't enable BGP on the interface and say, hey, I want to route with this connected neighbor on that particular link. We need to specify within our BGP configuration who the TCP destination is. Who do we want to establish a TCP peering relationship with, assuming we already have some sort of underlying transport mechanism in place. Like I said, BGP is not a routing protocol. It's an application to exchange reachability information. All right. BGP has different types of neighbors. Neighbors are not going to be discovered by default, so we don't just simply enable the protocol on an interface and then we go out and discover our neighbors automatically. Neighbor relationships have to be manually configured. And unlike most IGPs, neighbor relationships do not have to be directly connected. There are some restrictions, specifically with regard to the time to live and eBGP peers versus iBGP peers. We'll actually see that today. That's one of the things I wanted to kind of configure for you guys as part of this process, is to show you that limitation, if you will, with regard to establishing eBGP pairing relationships. Okay? As long as we have some sort of TCP transport, we should be able to establish a peering relationship with that particular neighbor. All right? That's the main goal. Always verify your underlying transport first before you actually go in and try and establish an adjacency. If we had some sort of router in Amazon Cloud or Azure or whatever, and we want to peer with them, as long as we can ping them, we should be able to establish a session. It's not always guaranteed, because there could be reasons why we can't establish a session. Other than that, maybe an access list or incorrect configuration, but we want to at least make sure there's some sort of reachability. In fact, I'll demonstrate in our lab portion today, having reachability does not necessarily mean you're going to be able to establish a peering relationship. The main thing to take away from this, though, is that BGP does not understand the underlying topology. Okay? So if you have some sort of multi-hop scenario, BGP is going to have to pass information down to the IGP process in order to establish some sort of adjacency. All right? And then also, of course, to be able to do route recursion and traffic forwarding. Okay? The BGP process is going to be used to exchange all of this application information. We use TCP port 179 with a unicast source and a unicast destination for transport. So again, unlike most of our modern IGP protocols that make use of multicast, BGP is only using unicast. So that means that we need to make sure that we have some sort of underlay reachability before we try to add our BGP overlay. Okay. Now in the case of eBGP peering relationships, for the most part, that's going to be directly connected because typically we have some sort of directly connected link to that neighbor, like a Metro Ethernet link or a DS3 or something like that. And we simply want to peer with the other side of that physical link. It's not always the case, though. In fact, we're going to demonstrate both scenarios tonight in the last part of our lesson here, when we talk about the difference between peering between loopbacks and peering between physical interface IP addresses. Okay. The BGP neighbor statement tells the process to listen for the remote address through TCP port 179. So it's actually enabling a service on the router, much like you would do with a web server or a telnet or FTP server. When you enable a particular service on that platform, you're actually enabling that process on that platform. All right. Basically, we try to initiate a session to the remote address that's specified in the neighbor statement through TCP port 179. Now, if a collision occurs where both routers try to claim or establish that client-based session, we need to have a speaker or a leader in that communication process. We call that a collision, by the way, where both routers are trying to become the TCP clients by sending the SYN request, but only one router in a BGP peering relationship can act as the client, and only one router can act as the server. In the case of a BGP collision, the router that has the higher router ID becomes the TCP client. All right. So what we're doing is essentially binding a socket. Like I said, it's like turning on Apache for a web service, and then we listen for incoming connections for TCP port 80 for those web sessions, right? It's a little bit less generic because BGP doesn't just simply allow any TCP 179 session to be established. BGP has strict rules about what neighbors can come in and how we match them against the socket information. Meaning to say that if I specifically issue a neighbor statement for, say, 1.2.3.4, I try to establish a session to 1.2.3.4, and I'm looking for connections inbound from specifically 1.2.3.4. All right? So for this reason alone, it's extremely important that clients and servers agree on the address that they're using for peering. The TCP SYN request has to match the address that's configured locally on the router. That's the most important thing. All right. We'll actually see what happens in our Wireshark capture. I'm going to demonstrate what happens when that's not the case. All right. If you want to see, I'll try it. I'm not sure if our viral images are going to run this, but show control-plane host open-ports. I'll show you that command a little bit later on. Should show us that we're listening for TCP port 179 connections based on the fact that we've configured a BGP session. So the local control plane packets come from the outgoing interface. This is standard behavior with BGP, right? I mean, with any packet, this is standard behavior. If I'm generating a datagram from a router, the source of that datagram is going to be typically the exit interface of, whatever interface that packet goes out of, right? So that could be so if I'm generating a datagram like a ping or a trace route, the exit interface that ping or trace route goes out of is going to be the source of that particular packet, right? So we need to identify either using the update source command if that's going to change. I'll show you guys that in a little bit. We need to identify what that source is going to be, or we need to just make sure that the packets, the Bgp open messages and the TCP SYN requests are coming from that particular interface, and that's our peering address that we're trying to establish a peering relationship with. All right. So sockets should only be bound to the unicast neighbor specified under the process. Clients usually source those from outgoing interfaces based on the routing table, and we can change that behavior using the update source on a per neighbor basis. I'll demonstrate that in our topology today. Okay. When the router decides how to send the packet based on longest match routing, typically it's going to be based on some sort of directly connected interface for that outgoing packet. All right. If we want to source the packet from a loopback and we want to send the packet to a loopback, the clients have to agree on those peering addresses to be able to identify the appropriate address that's being used for that peering relationship. Okay. Again, we're about to the point where we're going to start doing our demonstration, but I just want to reiterate, we'll take a look at this in a little bit. Okay. In fact, let's take a look at our topology right now real quickly. I actually have a couple of configs that I have to paste in here, so because I haven't actually configured any of these. So let's go ahead and give this guy a host name. Hostname R4, interface loopback 0. We'll put this in here because we're going to use this a little bit later for doing some peering. Interface gig 00. And let's do a no shut on that interface. And we're just going to set up a link here. So let's say between router 4 and router 5, this is 172.16.45.0. So I'll just make the router on the left .4. So IP address 172.16.45.4/24. And we'll do the same thing on router 5. Hostname R5, interface loopback 0, IP address 5.5.5.5. I don't know why it's running so slow today. It's weird. Interface gig 00, no shut. IP address 172.16. Oops. 45.5. 255.255.255.0. Oops. IP address 172.16.45.5. All right, so I should be able to ping 172.16.45.4. Why is it running so slowly today? There we go. Something really strange going on with these platforms here. We'll see if we can struggle through with it today. I don't know why they're running so slowly here, but show IP interface brief. So we've got our basic underlying transport, if you will, established. Interface brief. We've got our... This is going to be really annoying today. Show IP interface brief. Oh my goodness. Show IP interface brief. All right. So just two interfaces, really, really simple configuration, a couple loopbacks and our transport in between. Now, if I was going to create a relationship between these routers based on this topology, I would, of course, make this would be an eBgp peering relationship because we're peering between two different autonomous systems. So we would identify this essentially as eBgp. Let me stop some of these other routers. I don't usually have too much of a problem running these routers here, but let's kill some of these. We're not going to use these routers in our topology today because we'll use these later to establish some iBgp relationships. All right, I don't think that's going to help, but there's something else going on with my processes here. All right, so as far as the Bgp pairing types go, it's pretty straightforward. External Bgp peers means we have neighbors in different autonomous systems, which is in this case we do. Internal Bgp peers means we have neighbors in the same AS. It's really, really critical to understand the selection process or the configuration. Update, pass selection rules, those are going to change depending on what type of peer a route is being sent and received from. All right, we are going to go into this in a lot of detail, just not today. All right, the rules are significantly different based on loop prevention mechanisms, based on how the routes are advertised, how attributes are listed inside the updates or inside that network layer reachability information. And we are going to talk about this in much more detail later, but right now our focus is primarily on general transport and how do we handle general transport between the different peers. All right. For example, one of the most significant differences from a general transport perspective is that iBgp peers use for the TCP messages use a time to live, of 255, and eBgp peers use a time to live of 1. That's pretty significant, meaning that eBgp pairing relationships by default have to be directly connected. This is a behavior that we can override and we can change, and we actually will in this particular lesson because it is something that you guys have to be aware of. That is definitely something that you would potentially see on the exam with regard to issues with BGP, specifically issues with that time to live value. So I'm going to show you guys how we handle that. All right. So we're going to start with doing some basic peering between router 4 and router 5 on our Ethernet connection, our gigabit Ethernet 00 connection. But before we do this, we need to make sure that we have basic underlying transport. And the simplest way to do that, do a ping, do a show IP route, based on what we're trying to establish or how we're trying to establish that link. In this case, the 172.16.45.0 link, which is directly connected to gig 00. Okay. Router 4, we're going to go ahead and put that in autonomous system number 4. Router 5 in autonomous system number 5. We're going to do a packet capture. So let's go ahead and start. Before I actually do the configuration, let me start the packet capture on this link because I want to look at some things based on having BGP configured on one side of the link but not necessarily configured on the other side of the link. How is that going to manifest itself in the TCP establishment process? How do we identify that with the wire short capture and so on? And then we'll go ahead and do our final configurations. Just from a time perspective, we're getting pretty close to the end here, guys, so hang in there. I know we're maybe a little bit longer than 15 minutes, but I wouldn't think it's going to be much longer than that. Okay? So let's wait for this capture to start, and then we'll go ahead and start by configuring the BGP process on router 4. We'll do that globally, and I'm going to use the the 4-byte option, 4-byte format, as opposed to the 2-byte format. So we'll go ahead and filter out these messages here. We don't need to see this stuff. Apply filter not selected. Let's do apply filter not selected. And for loopback, let's do a filter down here. All right, so let's go ahead and set up our BGP on router 4. Config T. router BGP. So you'll notice here that we do support both values. We can either specify the value as a decimal value. That's what we see in the top, 1 to 4.2 million, whatever. And then we can also specify it as AS dot notation or ASN dot notation, where we have 1.0-XX-YY, meaning that our ASN can be written as like 4.4, for example. That's what we'll use in this particular case. All right. The router doesn't really care how you note the value, whether you do it in decimal format or the other format. There's really no difference from an operational standpoint. It's just a matter of whether what number is easy to read versus what number is not easy to read. So let's say, for example, if I want to go ahead and set the ASN, I'll just go ahead and specify 4.4. We'll go ahead and specify our neighbor. And in this case, we're going to do it to 172.16.45.5. Remote AS in this case is going to be 5.5. Okay. Now, before we configure anything else on the other side, let's see what the router did on the process. First thing I might want to look at, I don't know if it'll work in this version of iOS, but let's try it. So control plane, host open ports. And we should see that we are now listening for BGP sessions, right? TCP port 179, meaning that we're listening for anybody that wants to speak to us as a client using TCP port 179. All right. But let's take a look at the capture as well, because we should see in the capture that the router is trying to establish a TCP state with router 5 based on the peering configuration that I specified. We can see it send, reset, send, reset, send, reset, send, reset. So essentially what's happening is I'm sending a unicast TCP message. We can see that the transport is in fact TCP. Notice the time to live here is 1. We didn't specify that. It was automatically assumed because my autonomous system of 4.4 was not your autonomous system of 5.5. So I didn't specify specifically that this was an eBgp pairing relationship. It's just a matter of the fact that I've set up a neighbor with a different autonomous system than my own. BGP recognizes that as an eBgp peering relationship and automatically sets the TTL to 1. Okay? Notice the source and destination are unicast. And if I look at the TCP transport information, it's pretty straightforward, right? Source port is some ephemeral random port. Destination port is 179. We can see this is a SYN request. 24-byte header length. So we do have some options, 4 bytes of options. And specifically in this case, we're specifying a maximum segment size of 1460 bytes because we still have to account for the IP header and the traditional TCP header because we have an Ethernet of 1500 byte MTU. So we're accounting for, at layer 4 anyway, accounting for that extra overhead. All right, but this is pretty much what's going to happen. It's going to stay in this state. Now, if I do a show Ip Bgp summary, we can see that we are, in fact, in that idle state, meaning that we've never established any kind of adjacency with this peer. I've never heard any TCP messages from this peer. And if I did a show control plane host open ports on the other router, I'd see that TCP port 179 is not even active, which is why we're getting those resets. Basically, this device is saying, I can't talk to you on port 179. I'm not listening to port 179. Okay? So that would be one of the symptoms you might see about, with difficulty establishing BGP peering relationships is that you have an issue with even establishing that initial connection based on the fact that BGP is not configured on the other side. All right? The source and destination are unicast. We know that TCP transport protocols TCP. We have our standard IP header and so on. We can see the SYN request. I'm the client. I'm the one sending the SYN request. The server is going to respond with a, typically if it's configured correctly, with a SYN ACK, and then finally the server, the client will send a SYN message back to the server. We're not seeing that in this case. We're seeing a whole bunch of resets. So we're getting these resets because, and actually this is something you should be concerned about from a control plane perspective, because you could potentially, somebody could initiate some sort of denial of service attack against the control plane by sending a whole bunch of TCP sends on port 179. Yeah, you can. So from a control plane protection perspective, you may want to maybe block this information because it's again a way for us to be able to maybe overwhelm a router at the control plane. All right, now if I do a show run section BGP on router 4, show run pipe section BGP on router 4, one of the things you'll notice is that it actually lists, even though we did our AS dot notation for our autonomous system number, it actually identifies the autonomous system number using a decimal value. To me, it's a lot easier to read 4.4 than it is to read, you know, what is this, 262148. So the annotation isn't really correct in this case. I'll show you how we can change that in a little bit. You actually do that under the global BGP process. But before we do that, let's go ahead and establish our adjacency now by going into router 5 and setting up router 5. Config T, router BGP 5.5, and we're going to go ahead and specify our neighbor of 172.16.45.4, and we'll say in this case the remote AS is going to be 4.4. All right, now we should see in this case that there is an establishment. Notice it doesn't happen right away because BGP is a relatively slow protocol, okay? But eventually we should see the neighbor come up. Actually, that was pretty quick. And we do our basic verification by doing a show Ip Bgp Summary. So if we look at the show Ip Bgp Summary output, this is a very quick way of verifying whether or not you have an adjacency. Notice the AS is still established in decimal format. Again, I'll show you how we can change that behavior. But we see an up-down status of 6 seconds here based on when I ran the command. But this is really one of the most important columns here. The state prefixes received. Now I haven't received any prefixes because BGP peers don't actually exchange routing information automatically. You have to have network statements in order for the routers to exchange routing information. This is a very unique behavior to BGP that we didn't see with IGP protocols as well. In IGP, if I establish an adjacency, I exchange everything in my database, in my RIB. And I do that automatically. With BGP, not so much. All right. Let's change the behavior of the notation here. So I'm going to go into, oops, what's going on there? Config T, router BGP 5.5, and I'm just going to come in here and say BGP AS notation dot. All right, now if I do a show run pipe section BGP, I should see my original dot notation. Let's do the same thing on this side. Router BGP 4.4 BGP AS notation dot show IP BGP summary. Right. So now we are getting our dot notation, our AS dot notation, as opposed to the decimal notation. It's probably not something you need to really concern yourself with too much, but a lot of times reading the dot notation is a lot simpler than reading the decimal notation when you're trying to reference 4-byte ASNs. Okay. We're not routing because we haven't issued any network statements. We'll talk about that in another lesson in more detail. But again, BGP, just because we have a BGP session does not mean we actually are routing information. Zero prefixes is okay because we're not sending any information. All right, now if I go back and look at the capture, what I want to see in the capture message is, in the capture are all the different message types. All right, so here's all the messages that were failing. And then you'll notice, as soon as I went into the configuration, starting from this packet here, we actually were able to establish the session. We had our SYN, our SYN-ACK, and our acknowledgement. indicating that we were able to establish the three-way handshake. The peers are able to talk to each other. Now, there's nothing in those packets or in those segments that are specific to BGP. They're just basically standard TCP transport messages that allow us to establish a TCP session between the peers. All right, and we will take a look at what happens beyond that. Right, the next thing that we see is the open message. So let's go ahead and take a look at this. In the BGP open message, we still have a time to live of 1. We can see that it's TCP data. But if we go back to our notes here, we can see from the open message, where was that? Message types, right here. In the BGP open, we should see version, we should see my autonomous system number, hold times, identifiers, optional parameters, and so on. So if I go back to my capture here, sure enough, in the open message, let's scroll down. In the BGP open message, there's the marker field, which is all ones. We talked about that. It's gonna be all ones for newer versions of BGP. There's our linked message. So every BGP, this is essentially the BGP header. These two fields right here. Every BGP message, whether it's notification, open, update, etc., they're gonna have that particular header information. This is type 1, which is our open. If you look at, I wrote those down here. So BGP open is type 1, update is type 2, notification type 3, and so on. So we can see what type of message this is. And then we get our data. So this is BGP v4. This is my autonomous system number. This is the attribute that we talked about, AS_trans. We'll get into that more detail when we get into the attributes. Default hold time, 180 seconds. This is the router ID, happens to be a loopback interface, so we know that that was selected as the router ID. And then we have optional parameters. And then under the optional parameters field, this is all of our capabilities. So these are our capabilities. So we're able to do multi-protocol extensions like v4, v6, unicast, multicast. We can do route refresh. We can do route refresh. Let's see what else we got here. We'll get into a lot more detail about capabilities, enhanced route refresh, and what's the last one we have listed here? Support for our 4-octet ASN. So both routers are essentially saying, this is what I'm capable of doing. So when you communicate with me, make sure that you understand that these are, you can use a 4-byte ASN. I understand 4-byte ASNs. We can do enhanced route refresh. We can do basic route refresh. We'll talk about those enhancements a little bit later on. It's kind of beyond the scope of what we're doing today. Okay? So we see the three-way handshake prior to the open message. The open message, of course, has all the information that we talked about. Now, if I look at the capabilities exchange, I'm looking specifically to where I see AFI of 1 and SAFI of 1. Let me go back up here and show you, because that's essentially what it's telling me in this particular case. It should be right under here. Yep, AFI of 1 and SAFI of unicast. So basically this is telling the peer, hey, I support and I understand global unicast routing, specifically IPv4 global unicast routing. Now when we start to add v6 and other technologies or applications like MPLS, we'll see extensible information in there for those pieces of that information as well. All right, those things don't happen automatically. You have to turn them on. Sorry, that's my son ringing the doorbell. You have to turn them on, but we will actually see that when we go into some of our future lessons. Okay. There's a lot of other capabilities. Route refresh, the support for 4 octets, like I said. Once the peering is established, we should see these details also in the show IP Bgp neighbors output. Show IP Bgp neighbors. Now this is a much more robust output, if you will. I tend to try and stay away from this one unless I'm looking for something specific. But I do see the neighbor. I see the remote AS, which is now written in the AS dot notation because of that command we executed. This is pretty critical here. The BGP state is established. We also notice that the hold time and the keep alive interval, right? These are default values, 60 and 180 seconds. And we also see all of our capabilities, all right? So we see here, not multi-session capable. Route refresh is supported. 4 octets ASN is supported. Address family IPv4 unicast is supported. Enhanced refresh capability supported. So essentially, we're seeing what we would have seen, in the Wireshark capture. Also, look, this is a really important component as well, right? We don't want to see this number going up significantly. That means that we're having issues with BGP. Opens, we should only see a minimum number of opens because opens are only sent when you're establishing the BGP pairing relationship. They're not going to be sent beyond that unless you reset the relationship. Route refresh, possibly if you're changing attributes or policy. Keep alives should be incrementing pretty significantly. Updates probably should not be incrementing that significantly either unless you're adding additional network layer reachability information and so on. Okay. All right. There's a lot of other stuff you can see in this output. Like I said, we'll get into that in more detail as we kind of go into some of our other lessons. All right. Now, let's say I wanted to change the values. Remember I said that the lowest value gets negotiated. So let me prove that by coming into my BGP process, router BGP 4.4. And I'm going to say timers, BGP in this case, we'll just do 5 and 15. It'll give me a warning, but we'll do 5 and 15. That's my keep alive and my dead timer. And I'll do a clear IP BGP star. Be very careful about this because this is generally a resume generating event, meaning that you don't want to run this in a production environment. But if I go back to router 5...
What's the safe command? I know there's a soft in or out.
Yes.
Or what's the preferred way to do it? So that either you only affect either that neighbor or that.
What you just described is exactly what it is. You can do a soft reset for inbound, outbound for all neighbors, or you can specify a specific neighbor by its neighbor ID. Right, and I'll show you that as well. The command specifically is it's the same clear command, but in the case of a specific peer, you're doing like a clear IBGP star out or a clear IBGP star in, or you're doing a clear IBGP x.x.x.x in or out, depending on the peer itself. Okay, and that will.
What if I'm using the keyword soft?
Well, we'll talk. There's a difference between doing a clear and soft reset, and we'll actually talk about those differences in our next lesson. We're going to go through IBGP and eBGP enhanced relationships or enhanced an advanced discussion. I'll talk about doing soft resets and what that does specifically in those cases. But it's usually we're only going to use those scenarios if we're just changing attributes for prefixes that we already know. Okay. It doesn't, it maintains the TCP session, so we're not losing that TCP session, but we want to make sure that we understand what the new attributes are for those prefixes that are being advertised by the peer. And that's where a soft reset comes into play. Okay. If I do a show IP BGP, but we will get into that in a lot more detail. I'm trying to get this one wrapped up here. Because I know we're getting into an hour and a half, so at least on the recording anyway. Let me do a show IP BGP neighbors. And we can see now that the timers have been actually negotiated. This is not the router that I changed the timers on, but I've accepted those timers. And if you go a little bit further down, somewhere in here, I'm not sure where it is, but I believe somewhere in this output it states what my configured timers are versus what the received timers were, and I may have to look at a different output for that. But in any event, we accepted the lowest value based on the based on the pairing relationship. Also, one thing I want to point out here too, I just noticed this on the screen. You can tell who the client is and you can tell who the server is based on local port versus foreign port. Which one of these do you think is the server? I'm on router 5, by the way. Router 4.
Local port.
Local port is the client, right? Just like me establishing a web session to a web browser, I'm going to use an ephemeral port as my source port, and I'm going to go to the well-known port as my destination port, and that would be the server, right? So, and in this case, because router 4 basically had BGP configured first, it became the server in this particular case, but the foreign port identifies that router 4 is the one that's listening on TCP port 179 because that's the destination port. Only one router can be the client, one router can be the server. Okay? Now this capabilities exchange only happens with the open message. All right? This is where we say what we need to support in order to become peers, etc. All right? In order to kind of negotiate that, though, you have to get those open messages, which means you have to do some sort of refresh. Now, enhanced refresh means you don't necessarily have to drop the neighbor relation. So only one router can be the client, one router can be the server. But what I was saying about those open messages is because that's where we exchange our reachability, our capabilities. That's where we do our capabilities exchange. You have to clear the peer in order to be able to get that open message. And a clear IP BGP star does do that because it sends a TCP closed message, which means that we're actually removing that session. Now, enhanced refresh capability, which is what I was saying before my son was yelling, it means that you do not have to drop the neighbor relationship to see those new capabilities of the peer. Most modern BGP routers support this functionality. So you might do a clear in or a clear out, and that doesn't drop the TCP session, but it does allow us to reapply policies in a non-disruptive manner. Okay. If I do a show IP BGP neighbor, I can also see things like what prefixes am I sending, what prefixes am I receiving. We can see that we're running address tracking for faster convergence. We'll talk about address tracking in advanced sections of BGP. They used to have for fast convergence in BGP, they used to have something called a BGP scanner. And they replaced that with NHT, which is called the next hop tracker in some of the newer versions of code. Basically, it means that BGP is not going to wait for 60 seconds to clear the routes if a neighbor's lost. And in the past, the scanner would actually have to walk the table again after that process. We also see MTU discoveries, path MTU discovery. Let me scroll up here and see if we can see that. I should see it somewhere here. Somewhere in here, it's going to identify the MTU information. 30 seconds. Here, let's do this. Let's do pipe include MTU. There we go. Yeah, right here. This is what I was looking for. Specifically, that path MTU discovery is enabled with this pair, meaning that we can identify what the MTU of the segment should be as I'm sending and receiving information. All right. I still have to keep in account that we have an IP header and a TCP header and so on. Whenever I'm generating update messages in BGP, I want to make sure that I essentially have as much information in that packet as possible so that I can have fast convergence. But what happens if it's not configured correctly? And this is the last thing that we're going to talk about before we kind of wrap up for today. So I appreciate you guys sticking around. Let's say, for example, I don't want to peer between the physical interfaces. I want to peer between the loopback interfaces. So what I'm going to do is I'm going to go ahead and configure Eigrp. Let's just do ASN 100. And I'm going to enable this on my loopback interface. And I'm going to enable it on my my physical link between my peers. Actually, yeah, let's do that. Yeah. And we'll do the same thing on router 5. Router Eigrp 100. Obviously, I'm only doing this as a demonstration. We wouldn't be running an IGP between two ASs, but I just want to show you a couple of things here. So let's do a network of 5.5.5.5, and let's do a network of 172.16.45.0. So we should get an adjacency, and I should have reachability between my loopbacks. So if I ping 4.4.4.4 from 5.5.5.5, I should have reachability, which I do. Okay. So now if I go into router Bgp 5.5, and I'm going to do a no neighbor 172.16.45.4 remote AS 4.4. And I'll do the same thing on router 4. Bgp 4.4, no neighbor. 172.16.45.5, remote AS 5.5. So do show run pipe section BGP. If you look at this config, I basically just have BGP running, but I haven't identified a specific neighbor. So let me go ahead and specify the neighbor now by doing a neighbor. We've already verified that we have reachability, which could be done with static routes or any other type of route. I want to set up a neighbor relationship between the loopbacks using the same remote AS. All right. Now, if I go back and I look at my packets and I look at the captures here, all right, we're seeing the send and the reset. And what's happening in this case, let's filter out our Eigrp, apply filter and not selected. Okay, is, let's make sure that's the right, let me see if this is the right information. It should be the right information. Destination 45.4, 45.5. That's not correct. You see, we should be seeing messages going to 5.5.5.5. Let me do a quick show IP Bgp summary on the router. Well, clearly this is not going to work for a couple of reasons, but we'll go through that in a second. Let me do a show IP Bgp summary. Okay, so it is definitely going to 5.5.5.5. I'm not sure why I'm not seeing the messages, but it's in idle state, right? And we've never established a relationship. And if I do a show IP Ceph for 5.5.5.5, we can see that we're matching the 45 link, okay? Which means that the traffic is going to go out of gig 00. It's going to go out of gig 00, which means it's going to be sourced from 45.4. And then the traffic will be routed to 5.5.5.5. So because I've configured neighbor 4.4.4.4 on the other side, even if it did get that TCP open message or that TCP send request, it is not going to allow that session to be established because it doesn't match the socket information that we've configured in the neighbor statement. So what I'm going to do is I'm going to do a neighbor of 5.5.5.5, and I'm going to say update source loopback 0. Well, we can specify all of our interfaces, but I'm going to go ahead and just do loopback 0, which means now my BGP open or my TCP messages are going to be sourced from 4.4.4.4, and they're going to go to 5.5.5.5, which means I should be able to establish a pairing relationship. Now, let's see if we're seeing those messages this time. Still not seeing those messages. I think that my captures are messed up here. You get the idea though, right? Those messages should be coming from the loopback going to the loopback. That's what we're looking for specifically. I'm not sure why we're not seeing them here, but we'll continue with the process, the configuration process. So if I do a show IP Bgp summary, and I take a look at the configuration, I can still see. Let's see if we can go ahead and start the capture again, because we are having another problem. Yeah, actually can put it in the notes. It's eBgp, which means our time to live value is 1. And we're trying to go from a loopback on router 4, which is essentially 1 hop away, to a loopback on router 5, which is also 1 hop away, which means that we're running multi-hop BGP. There's no way for me to establish a pairing relationship between these routers because the packets are not being routed. They're being dropped because the time to live is being exceeded. All right. So Wireshark is not working, so we'll just go ahead and kill that for now. Next lesson I'll actually show you. For now, you just have to kind of believe me, but there is a way to fix this problem as well. If I do a show run section router, we can see it's a pretty basic configuration. We've identified where the packets, BGP packets, are coming from, loopback 0 in this case, and where they're going to, which is our other loopback. We've already verified our underlay network is working correctly. So the next step is to specify neighbor 5.5.5.5, and we're going to do a eBgp multi-hop, and we can specify the hop count. I believe if we just hit return, it will go up to 255. Let's just go ahead and set it at 2. Okay, meaning that we're now allowing more than 1 hop for these eBgp messages to go across that link. All right, maximum is 255, of course. You would set this value to whatever you want. You don't have to worry about this in Ibgp, because in Ibgp it's already set to the maximum value. You could limit the scope of Ibgp by specifying the Ibgp hop scenario. We're not going to be able to establish the adjacency here, all right, because again, we have to look at where the messages are sourced from and where the messages are going to in this particular case. All right, so let's go ahead and duplicate that configuration here. Router BGP 5.5, oops. Let's go ahead and set up our neighbor 4.4.4.4, remote AS, this guy's 4.4. And we'll do the same thing. We want our configuration to be consistent. We'll go ahead and specify that we're going to use update source as loopback 0 in this case, and we'll also do our multi-hop. Technically, you don't have to do this to be able to establish these adjacencies, because once I get a TCP message from one side, I should be able to respond to that TCP message, but we do want our configurations to be consistent. Show IP Bgp Summary. We can see now that we've established an adjacency. All right, so we'll get into a lot of stuff, a lot of other configurations as we go through the rest of our lessons. This is just kind of an introduction. But you know, that's pretty much it for the basic stuff, right? In our next lesson, we're going to get into some of the advanced configuration options between iBGP peers and eBGP peers, and how policies get applied between those two different types of peering relationships. All right, we'll continue to build on our topology, and we'll continue to make kind of add to our topology so we can see some of the constraints and some of the requirements that we have for establishing these pairing relationships. All right, so that'll be our next lesson, which is iBGP versus eBGP pairing rules, and then we'll look at establishing a full mesh. What are some of the scaling techniques with things like route reflectors and so on, and then we'll get into configuring route reflectors and confederations. A lot of good stuff coming up with BGP. All right. So if you guys don't have any other questions, we'll go ahead and wrap this lesson up for tonight. We'll see you guys tomorrow, actually. I'll send some Slack messages and we'll get into our next lesson for tomorrow. All right? All right, guys. See you next lesson.